Hi everyone, welcome to my YouTube channel tutorial on my table. And today I will discuss the semiconductor physics part 2. I have already discussed the semiconductor physics part 1. In part 1 I have discussed the syllabus of analog electronics and classification of temperature. In semiconductor physics I have discussed the classification of temperature and the thermal voltage or voltage equivalent of temperature. If you have not watched that video yet, please watch that from the link in the icon. We start to discuss the semiconductor physics part 2. In semiconductor physics part 2, I like to discuss. At first, I like to discuss the band diagram. Before starting band diagram, I I will show the graph between the electron volt and space. Means electron volt in y-axis and space in space in x-axis. So let's draw this graph. In this axis, electron volt, and in this axis, phase. This represented in AC, and this represented by AC. This is conduction band, and this is valence band, and this gap is AC. Is equal to AC minus AC. So the actual picture is this is CP or conduction band, and this is PV or valence band, and this is the band gap. Band gap. Here CP is conduction and PV is valence band. Here this is all here band means and band means group of energy. And here the voltage is EG, energy gap. In here you have to know the relation between EG and temperature. Here temperature in Kelvin. Kelvin. The relation is a relation between EG and EG equal to EG 0 minus beta t. Here beta equal to material constant Ag equal to Ag in T Kelvin, and Ag 0 is Ag in 0 Kelvin. Okay, so here you have to remember some value of Ag in room temperature and 0 degree Celsius for 0 degree Celsius, sorry, 0 K in for germanium and silicon. So let's discuss the value. So I will discuss the Ag0, and it is 0.785 electron volt for germanium Je, and 1.21 for silicon. Value of Ag at infinity. Ag thinks of it is 0.72 electron volt for germanium and 1 point, sorry, so it is 0.72 electron volt for germanium and 1.1 electron volt for silicon. So the energy gap Ag decrease with the increase in temperature. As linear variation, linear growth. So now I discuss the electron volt. Electron volt. In semiconductor physics, semiconductor physics, the practical unit of energy is called electron volt. It is also defined as then the energy gained by electron in moving in a potential difference of 1 volt. That if the direction of electric field is from plus to minus, and the direction of moving electron is in the opposite direction of electric field. The movement of electron is opposite direction of the electric field. Here the electron moves from here. The electron moves from negative to positive. So here electron lost potential energy and gain kinetic energy, or K. The gain of K is equal to the loss of P. Here K is kinetic energy and P is potential energy. So half m v square equal to qb. Here v is the velocity of electron and m is the mass of electron and q is charge of electron and v is voltage of electric field. Here I will write in the mass of electron and velocity of electron and q charge of electron and v voltage of electric field. So from this relation we calculate the value of V. Value of V equal to root over 2 QV by M. So the relation between velocity and voltage is V equal to 2 QV by M. Now I have discussed the electric field. Or electric field density or field gradient or field. It is denoted by E. Here E is defined as the ratio magnitude of existing voltage voltage divided by spacing or distance. Spacing or distance. The unit of E is volt per meter. Here I would like to give an example of electric field and just analyze it. So I will give an example. This is his example, not energy efficiency. Okay. Let's an uniform electric field, a uniform semiconductor. Let's take a uniform semiconductor. Let's take a uniform semiconductor. This uniform semiconductor is driven by a battery of sodium. Then driven by a battery of 1 volt. Battery of 1 volt. So here the voltage will be rise. It is plus, it is negative. Here voltage rise. I take 3 point, A point, C point, and B point. This battery is the magnitude of this battery is 1 volt. So in A point the value of voltage is 1 volt, and in B point the value of voltage is 0 volt. But so the voltage of B is 0 and C is high. The voltage of B, it is the voltage of B, and here voltage of A. In A the voltage is 1 volt. 1 volt. In B the voltage is 0 volt. 0 volt. And this middle point is C. In C point the value of voltage is 0.5 volt. Here the voltage is different, but how E is same. So in A point, the magnitude of E is 1 volt. Distance from here is 1 mm. Let's take this distance is 1 mm. Let's the breadth of this semiconductor is 1 mm. So the distance of B to this point is 1 mm. So here put 1 mm. So 10 to the 3 volt per meter. Now in B point, now in C point, in C point, value of E is 0.5 volt by 0.5 mm, or 0.5 divided by 0.5 into 10 to the power minus 3. So 10 to the 3 volt per meter. So the conclusion, is, so the main conclusion, so the note is on a uniform semiconductor, the field intensity will remain same. So next topic is mobility of charge. Mobility of charge. Mobility of charge is defined as mobility of charge is defined as mobility of charge is defined as the division of depth velocity to field intensity. So mobility to depth velocity Vt divided by field intensity. Now the unit of mobility is Vt divided by E. The unit of Vt is meter by second and E is volt per meter. So the unit is the square by volt second or unit square by volt second. Understand? The mobility of charge indicate how fast the charge carrier is moving from one place to another. This is the definition of mobility. The definition of mobility is indicate how fast the charge carrier is moving from one place to another. The definition of mobility. In semiconductor, there are in semiconductor, I will indicate the semiconductor in my whole lecture. Okay. So in semiconductor, the charge carrier is two types: electron and hole. So mobility in semiconductor is also two types. One is mobility of electron, and second one is Second one, mobility of hole. Mobility of hole. Mobility of hole. We denote the mobility as mu. We denote the mobility as mu. So the mobility of electron is so the semiconductor has two types of mobility. One is electron mobility, and second one is hole mobility. Second one is hole mobility. It is denoted by Ph or mu P. It is also or mu N. Okay. Here I will discuss some value of mobility in germanium or and silicon. The mobility of electron mobility for germanium is the value of electron mobility for germanium is 3800 square by volt second, and for silicon the value is 1300 square by volt second. And the value of hole mobility mu H or mu P for germanium. The value is 1800 square per second, and for silicon the value is 500 square per second. So from here you noticed that the electron mobility which is always larger than hole mobility. In exam point of view, you have to remember the ratio between mu n and mu p. The ratio of mu n and mu p is 0.1 for germanium and 2.6 for silicon. This value is important for the exam point of view. In GFCIL, this question is asked. Okay, for exam point of view, you have to remember the magnitude of ratio between mu n and mu p. Okay, here I like to discuss some properties of germanium. And silicon. Germanium is 18. You have seen from previous lecture that the mobility in germanium for both for hole or electron, for both the mobility of charge carrier in germanium is higher, so the conductivity in germanium will be higher. So I write here it has higher conductivity as it has higher mobility. Next point is it is relatively more used in higher frequency applications. So now discuss the properties of silicon. Properties of silicon. It is suitable to play in high power application. High power application. The leakage current in silicon, leakage current in silicon is very small. It's very small. The leakage current in silicon is in the range of nanoampere. But for germanium, it is in the range of microampere. And the next point is it is the and the next point is it has high temperature handling capacity. The second point is very important. Second point is main advantage of silicon over germanium. So now I will discuss the relation between mobility and temperature. Relation between mobility and temperature. Relationship between mobility and temperature is mu is directly proportional to T to the power minus m. Here m is material constant. The value of m is 2.5 for electron, 2.7 for hole. This value is for silicon and 1.66 for electron and 2.33 for all. The second value is for germanium. So, so the relation is if temperature increase the mobility okay, decrease, and also mobility has non-linear variation with temperature. So, I will end this lecture here. So thank you all. If you like this video, please like, share, and subscribe. And just